Hey there, folks. Happy Monday. It's time to move on to another topic in the rotation chapter that we haven't seen yet. Here's our problem. Imagine that we've taken a rod and bent it into the square shape that you see on the screen. Each side of the square has a length of a, and what we need to do is figure out the moment of inertia for this entire square frame that's relative to a rotational axis acting through the center. Now, this is not something that you would find in a table of moment of inertia values. In fact, as of right now, we can't even solve this. We haven't yet talked about the proper tool to handle such a situation, so we'll need to remedy that by introducing something known as the parallel axis theorem. And since our problem deals with a rod, let's go ahead and start with a regular, unbent, thin, uniform rod. Currently, we know of two locations that we can place a rotational axis in order to calculate the moment of inertia for this rod. One spot goes through the center of mass, which is being represented by that black and white symbol there. And the other spot is found at one of the ends, like here on the left, for example. Now, what if we want to rotate about an axis that's located somewhere else? Say here, at some displacement d from the center of mass. Are we allowed to do that? Well, the answer is yes, and the parallel axis theorem tells us how to calculate it. Now, just a small warning here, this is going to be a little wordy, but I'll try my best to make it straightforward. The theorem below states that the moment of inertia about a rotational axis that is parallel to a rotational axis that goes through the object's center of mass is equal to this sum on the right. And what are these two terms? Well, the first one is the moment of inertia about an axis through the center of mass. Okay, so like the first thing we saw, where the dotted line was going straight through the very center. And then we have a term here that's a product of two variables. Capital M is the object's total mass, and lowercase d is the displacement from the center of mass, right? So we calculate the regular moment of inertia relative to the center of mass, and then we take this product. We add the two things together, and that's it. Now you have the new moment of inertia located at this other position. Now, one thing to keep in mind is that the displacement, d, can be outside of the object, like this. I know that seems a little strange, but we're going to take advantage of that to solve our problem. The first thing we'll need to do is work with an individual side of the square, and then we'll take that result and use it to build the answer representing the entire square frame. The moment of inertia through the center of just a single side is given by the following expression, and that is actually found in our moment of inertia tables for different kinds of geometrical shapes. Since we're dealing with just a single side of the square here, we're going to need to adjust this result a little bit. This total mass, capital M, needs to be replaced by m divided by 4, since we're only working with one side of the square, and one side of the square has 1/4 of the entire mass. Additionally, we're told that the length of each side is given by a and not L. So let's go ahead and plug all of that in for this expression down below. So we'll be taking 1/12 times the total mass divided by 4, since we're working with one side, and we're multiplying it by the length of one side, a squared. The 12 and the 4 in the denominator here can be multiplied together. And we'll go ahead and squish this down into a more compact version like this. And so now we have the first term in the parallel axis theorem equation for one side of the square. Okay, so it's COM one side. And we're going to use this for the other sides as well. The next thing to do is to figure out what lowercase d would be in that md squared term. Here's a picture of our square frame with the center of masses labeled on each side. Okay? Now remember, I said that d can be outside of the object. And that's actually the case for the very center of the square frame. And if each side has a length of a, well then that means if we chop a side length in half, the displacement from the center of mass from one side to the very center is going to be a divided by 2. And in fact, because of the symmetry of this object, it's going to be the same displacement from all sides. Okay? Each center of mass to the very center will be equivalent to a divided by 2. So this means if we use the parallel axis theorem on just one side of the square, we can multiply the result by 4 to account for all of the sides, and then we're done. So let's move on to that part next. Here's our definition right up here at the top, just as a reference, and we're going to use this and plug in the values that we've found so far. So ICOM, center of mass, is going to be the moment of inertia for the center of mass of one side. Okay, so 1 over 48 ma squared, right? That m over 4 is incorporated into the 48, just as a reminder. And we said that d, the displacement from the center of mass to the very center of the square, is just the length of a side divided by 2. So, to move forward, let's go ahead and square this displacement term. And now we can take these two 4s in the denominator and multiply them together to get ma squared over 16 in that final term. If we want to add these two things together, they need to have a common denominator. And to find that, we're going to take the least common multiple of 16 and 48, which is 48. So let's go ahead and multiply this term here by a special form of 1 to also get it into a denominator of 48, right? So we'll take it, multiply it by 3 over 3, and so now they have the same denominator, and they can be added together nicely. Okay? And when we do that, we end up with 1 quantity of ma squared plus 3 of the same quantity in the numerator, resulting in 4 of that quantity upstairs. And we can also simplify the fraction of 4 over 48 down to 1 over 12. And so now we are done with one side. This is the moment of inertia using the parallel axis theorem relative to the very center of the square for one individual side. And so what's left is to multiply this result by 4 to get the moment of inertia for the entire square relative to the center. And so we just take 4 times ma squared over 12, and 4 over 12 can be simplified down to 1/3, and now we're done. And we can officially say that the moment of inertia of this square frame, the whole thing, about an axis through its center is equal to ma squared divided by 3. And that is how we apply the parallel axis theorem to problems like this one. I hope this helps. Have a good night, everybody.